start by summarizing what we learned in lecture 1. So as a summary. We discussed that when you use the conventional formulation of string theory, we won't be able to deal with the IR divergences properly. So IR divergences was the main reason for looking for a string field theory. So string field theory is a Lagrangian formulation of usual string theory, and if you have a Lagrangian formulation, we know how to deal with the IR divergences. And then we mentioned that a string field theory has complicated gauge structure. I didn't discuss this in detail. What do I mean by a complicated gauge structure? And we discussed that if you have relatively simple gauge theory, quantization of gauge theory or quantization of such gauge theory can be done using the Faddeev-Popov functional integration method. And in Faddeev-Popov, we saw that we start with a classical Lagrangian, and then we gauge fix it, and after adding certain auxiliary field, we get a new Lagrangian, which is the classical Lagrangian. And classical Lagrangian is constructed using the gauge field and matter field, and then we have a term corresponding to the gauge fields, and we have terms corresponding to the gauge fixing. And we added an auxiliary field H as well. So we had at the end, after gauge fixing and then after adding auxiliary fields, we have a gauge field, matter field, and gauge fields, and an auxiliary field. And then we said we found that we can find a transformation or a global transformation for these variables, and that will keep the new Lagrangian invariant. So that was the BRST transformation. So then we discussed that BRST symmetry is an important symmetry, it's a global symmetry, and that can relate Green's functions or correlation functions. So it provides you non-trivial relations between Green's functions. But such relations involve inserting BRST variations. So we had to deal with, so I denoted the collection of these fields by the notation chi tilde, and then we found that when you find such relation between different Green's function, we had to introduce a BRST variation of any of these fields inside the correlation functions, and then with that insertion we found a set of relations. And that relations were easy to state if you use the generating function. So what was the generating function? So the generating function was obtained after introducing a source for each field in your theory, including auxiliary fields. So we had generating function given by a path integral over dA mu, d psi bar, d omega bar, dh. Then we have the action. So you have new Lagrangian plus a source term. So we wanted to figure out what is the implication of PRST symmetry for this generating function. And we said that that's a Slavno-Taylor identity. Let me derive Slavno-Taylor identity for BRC transformation. And once we got the Slavno-Taylor identity, then we found another relation, which was the Singh-Justin equation. So let me derive the Slavno-Taylor identity. We can start with the generating function, and then say we can write it in a compact way as d of chi n e raised to I d for x L nu plus chi tilde n jn. So this path integral we are supposed to perform over the gauge orbit of chi tilde n. So we could choose another point in the gauge orbit, and then we can express this as d chi tilde n prime e raised to I d for x, and then L nu, which is a function of chi tilde n prime. Now how chi tilde n is related to chi tilde n prime? So this is a gauge fixed action. So they can't be related by arbitrary gauge transformation. These chi tilde n and chi tilde n prime are related through a BRST variation. So if these two field configurations are related by a BRST variation, then these two integration represents the same object, the same generating function. So that's a trivial statement. So we just utilize the fact that the functional integral is invariant under any of the field configuration. I mean, you can take any particular choice of the point in the gauge orbit and then perform the path integral. Now on the top of it, we demand that chi tilde n prime is equal to chi tilde n plus delta b. So from here to here is just a change of variable. Now we want to demand that chi tilde n prime is related to chi tilde n with the BRST variation. So just plug it into here, and one can argue that the measure is invariant. It's not straightforward, but one can argue that. And then it's easy to see that the new Lagrangian is invariant under such a BRST transformation. But there will be a particular term that's coming from the source term. So when I connect these two with this relation, you see that there's an extra term. L nu plus chi tilde n jn plus delta BRST variation of chi tilde n multiplied with the source. So except this term, everything is same as the original generating function. Now this means we assume that, let's say we do a small
Very basic question about the notation. This chi tilde is A and psi bar.
Yeah.
You have just gauge theory with matter in
Yeah, that was the example we discussed last time. So we took a particular theory having a Lie algebra, and then did the quantization. So there, in that theory, we just we have a gauge field and then this matter field psi bar, and these were the ghost fields and auxiliary fields. So for that particular theory, we were trying to derive the Slavno-Taylor identity. So what we can do is we assume that we do a small BRST transformation so that we can expand it. So the first term, it's easy to check that that's again the generating function. And the second term comes with the BRST transformation parameter, and then you get the source outside, and then we have to perform the path integral over d chi tilde n e raised to I d for x L nu plus chi tilde n jn with an additional insertion, that's the BRST variation. So that was the variation which we denoted as delta n. So let me mention that notation. So we said that delta, so let's say we want to do a BRC transformation with a parameter theta on a field H, then this is equal to theta into SH. S was the fermionic operator that we introduced, and we denote it by, so if it is chi tilde n, then we denote it by theta delta n. It's just a notation. So we have this insertion, delta n insertion, in the path integral. So this is basically an expectation value of this insertion, delta n. So you get the following thing. So you have first term as the generating function, and then you have I theta jn, and then the expectation value of delta n with source j, with the source j. So, huh? This one. So this is the path integral, right? So this is the expectation value.
Well, it should be usually integral d4x jfx.
That's true. Agree. So we see that we have the following equation. Take the expectation value of delta n and then multiply it with the source, then integrate over the space time. This should be equal to 0. Oh, delta n was this. So let's say we are looking at the field chi tilde n, take the BRST variation, and this is just a definition. Or you could just write it like S chi tilde n. So you can just write it. So this is the, so here the source is switched on. So this is a simple identity that we could derive, and then observe that, observe the following thing. So you can write the path integral or the generating function in terms of W. So this is the definition of W.